Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So let's get started. It's my pleasure to introduce Paul Shu. He is a PhD student at MIT with Jim Glass as his advisor. And this summer he worked with us. Before that, of course, he was in the speech product group for 4 years, so a lot of you, I guess, know him already. And this summer he did an internship with us at MSR, and he had a very productive summer, and he did a lot of work, and he has a very compelling prototype of multimodal text entry that he's going to talk about now.
All right. Good morning. Welcome to the presentation period. So as Milind said, I am currently a PhD student at CSAIL at MIT working with Jim Glass. And this summer I had the opportunity of working with Milind, Alex, and all of you on this interesting project where we try to combine multimodal input modalities together, specifically speech with keypad. This project actually started quite a few years back with Milind, XD Huang, and Kwang Sung, where they attempted to constrain the recognition results using keystrokes. This summer, we actually extended this modality to continuous speech recognition. We improved the UI, ported to the Pocket PC, and also improved its performance. So mobile text entry scenarios. Well, generally, the devices that we are mostly interested in are the smartphone with its limited UI. Namely, we have a few buttons, in some cases a keypad. The performance on these guys, we only have 200 megahertz to work with or so, with 64 megabytes of RAM. Pocket PC devices are a little bit better. We have 400 megahertz on average today, with twice the amount of RAM. In the next generation devices, so this will be in about 2 years with Photon, we expect the devices to be a little bit more powerful. However, at the same time, we would like to target a larger range of devices and not just the high end. So it's not clear whether we will have much more resources to work with. So in terms of application scenarios where text entry is used, SMS is the predominant application, with the SMS text messaging finally taking off in the US at more than 5 billion messages per month. It is kind of an interesting application to look at. How can we actually improve the rate at which people can type SMS messages? The format of SMS messages are generally kind of short sentences or phrases, generally conversational, fairly casual. And it is interesting what type of modeling we need to do to actually enable this type of scenario to increase the efficiency and the robustness at which people can enter these messages. Some of the other forms of text entry on these devices include entering appointment subjects or email subject lines. These are kind of similar to SMS messages in the style, but have a slightly different flavor. They're also kind of the web queries, which is kind of an interesting scenario that's being developed. And since the style of the language there is somewhat different, we will actually not focus on that too much in this presentation and leave that as future work. Email content and kind of document authoring on the devices is kind of interesting scenario, but it is not clear that the solution that we're proposing here is effective for these longer paragraph dictation scenarios where efficiency becomes more of an issue. The language is generally kind of is richer, and we need to perform a little bit faster. And of course, there are some cases such as voice dialing, entering the names of email recipients, address entry, where the grammar is somewhat constrained. For these things, a CFG-based, context-free grammar-based solution may be sufficient. So again, for this project, we focus primarily on kind of the free-form text entry, namely the SMS text messaging. In terms of the current input methods that are available on these devices, Multitap is, I guess, the most traditional. In this particular scheme, let's say we want to enter the word this. We would tap the key 8 once to get T. So notice 8 has T-U-V next to it. So we tap 8 once to get T. To get the H, we tap 4 twice to get the G-H-I. And 4 again 3 times to get the I, followed by 7 4 times to get the S. Now notice in this case, how do we know we have 4 4? Where do we actually put the break between the first 2 4s and the latter 3 4s? So for multitap, generally what happens is there is either an explicit character advance button, or there is a slight timeout in which if you just don't type anything, it will advance to the next character automatically. Now, as you can see, this is kind of slow. Fortunately, it is actually deterministic, so there are actually people who can type using multitap without even looking at the phone and author a message. I personally can't do that, but people like that do exist. And because it's deterministic, we don't have any issues of out-of-vocabulary words. You can type just about anything, even words that don't make any sense. Another input method that is fairly popular is the TJIC communication, T9. TJIC was recently acquired by AOL back in 1999. And basically, the idea is that instead of having to tap each key multiple times, let's just tap each key once. So for this, we only need to tap 8 4 4 7. And because the sequence 8 4 4 7 only has one valid English word, that is the one that the system predicts. Now, because of this predictive nature, there are actually some key sequences that actually have more than one word associated with it. So for example, good and home actually share the same key sequence as quite a few other words. So in these cases, we actually require an additional button that the user can press to choose the next guess as to what that particular word sequence is.
So it looks like P9 saves about 50% of keystrokes, at least for this
Yes,
example.
yes.
Do you know what the rate is in general?
That is actually approximately right. It's around half. Although in terms of time, it's not as clear. Because for me to press the same button multiple times, the amount of time to do that is different than to find, okay, where is S? Next button, and then press it. So in terms of time, it's not as clear. It depends on the user, whether you're a novice user or expert user. But in terms of keystrokes, it's roughly a factor of 2-ish. And with T9, because it kind of relies on a dictionary, there are these issues of out-of-vocabulary words. If I enter a word, let's say the word OOV, it's not going to have that in the dictionary. What do I do in that case? And generally, there are a few strategies for dealing with that. We will talk a little bit more about that later. There are a few variations of T9, in fact, even the later versions, the more recent versions of T9, that actually speeds up this even further by adding predictions. Instead of typing the entire word out, after just typing 844, it can predict, well, maybe the word you want is actually this. So you don't have to type the S to get that. Instead, you can just press, let's say, the right arrow key and say, I'm going to commit the predicted word. So this actually speeds it up a little bit more. And in many cases, this is quite fairly good. A kind of different modality that people have started looking at is actually using speech. Voice signals technology back in April this year introduced the voice mode technology. And this technology allows you to perform isolated word dictation onto devices. And so, for example, if I want the sentence, this is a test, what I would say is I hold down the button and start saying, this is a test, and watch the words appear. The correction experience is okay, but we feel we can do better than that. And of course, because it's based on speech recognition, the amount of time it takes to enter text onto the device is dependent, highly dependent on the recognition accuracy. Recognition accuracy depends on the particular acoustic environment, the user's voice, and many other factors. Therefore, it's kind of difficult to quantify how fast a speech-based modality such as voice mode will be in terms of entry efficiency. The table here shows the various bandwidths for various text input methods. So generally, for people using the keyboard, we can achieve around 50 words or so per minute for average typists. With T9, the predicted entry rate for expert users, assuming the first prediction generated by the system is actually the correct one, namely we don't have to actually select the next alternate, is around 46 words per minute, which is pretty good. But the assumptions are generally not valid. Oftentimes, you do have to select the right character, the right word prediction, in which case the user needs to look at the screen, press a few times, and it does slow the entry rate quite a bit. And that's also assuming you actually already know the keypad layout already. For me, when I look for the letter K, I have to search a little bit to see which button, which key the letter K corresponds to. So for novice users, we're not going to reach anywhere near 46 words per minute. We'll be lucky if we get 10. So this raises the question, are there ways of speeding up, of improving the efficiency of text entry? Now we look at this table. Ooh, speech looks pretty good. 250 words per minute. Now that number is just average speaking rate without correction or anything.
How about use of the BlackBerry when they have a keyboard? How many words they average?
I don't have the numbers with me, but that's something I can look up. I am estimating it is somewhere similar to 46. Because the basic idea is that this particular value is predicted assuming you have perfect accuracy from the prediction. So with BlackBerry, it takes a little bit more work to find the right key because there are more keys, but it should be close.
It's closer to QWERTY.
Sorry?
It's a QWERTY keyboard, like a...
Yeah, but it's smaller. It's significantly smaller. Yeah. So generally, we talk about two-thumb operation, and that is quite different. So an expert, maximum speed you can get on a BlackBerry-like device, I suspect is around maybe 40-ish.
So again, there seems to be a really high variance when I look at the two rows between what trained human can do and your average user.
Oh,
so
yeah.
the next two lines, are those for like professionals or
Which two lines?
Multitap and T9?
These are for experts.
Which should I those are experts.
Experts.
So that goes against the 150.
Yeah.
Yes, you should compare that with the 150. But even for the average typists, we're not even catching up to them. So there's still quite a lot of room for improvement.
Oh, it's not that far, 46 from 50.
The assumptions made for that particular prediction is that there are no errors in the prediction, which we know is generally not true.
Most people cannot achieve T9, 46.
I know. Yeah.
Well, that's also like, compare that to the professional. It's not 50 to 46, it's 150 to 46.
So in practice, expert typist, I'm guessing, achieves around kind of 30. I don't have real usage numbers for this. This is a predicted value based on the kind of the distance between the buttons and various other factors. So it's kind of like...
Love BlackBerry. People love it.
Yeah. I mean, it's still pretty good. We can do pretty good BlackBerry. I suspect on the order of 40 words per minute. So it's a pretty good.
My point is nobody loves speech yet.
Agreed. We hope to change that at the end of this presentation.
I
So-
said yet, right?
So speech is an interesting thing to look at. Can we somehow combine speech as an input method to increase the efficiency of text entry on these devices with limited input methods? How can we do it in such a way that we do no worse? So in the case with voice mode, if the accuracy is poor, you'll be spending all of your time correcting. And you actually do quite a bit worse than just typing out the sentence using, let's say, T9. So what can we do to actually make sure it's not any worse? So over here is our prototype application implemented on top of a Pocket PC. We call it SpeechPad. Essentially what it is a speech-driven technology to kind of improve the predictions of T9. So we use the speech results to improve kind of the word prediction capability of T9-based text entry. We can think of another way too. Instead of thinking of using speech to improve T9, we can think of T9 using the keys you press using T9 to kind of search through the speech lattice to constrain the speech results. Either way of thinking about it is pretty much the same. We'll take a look at this in a little bit more detail later. One of the assumptions that we have to make when people use these devices is that they're going to be carrying it to all sorts of places. The acoustic environment varies quite a bit. We could be in a quiet office, in a large exhibition hall with significant echoes, or we might even be in a running subway train, which is fairly noisy. How can we make sure that this method will work in nearly all of these different acoustic environments? How can we make sure that we can handle and be robust to speech recognition errors, which are bound to happen? And just for those who are interested in the underlying technology, this application is built on top of Yakima CE speech recognizer. Currently, it has a 9 megabyte footprint for the language model and the core algorithms, consisting of 30,000 word vocabulary using a speaker-independent model. So let's take a look. So over here on the left side, we have the record button. This button kind of differs in position for various different devices. On the Dell here, it's kind of lower down near the middle, which is kind of unnatural, but that's where this particular device is. So we hold down the button, and we start talking and saying the phrase. This is a test. So notice what we see here is the word this showing up as the prediction for the first word. Some of the other predictions that we see here are this, of, list, vistas. So we can use an up and down arrow to select the prediction. So let's scroll back to the word this and click the OK button to commit it. And this will insert it into the text window. And notice the word is correctly recognized, so we just commit that, a test. Let's take a look at a little bit more of speech recognition. So again, we have of speech recognition. Now, in meetings, such as, let's say, during this presentation, if you want to actually enter text, you don't want to actually speak the text. So the particular interface here allows you to fall back to just text-based entry without having to make an explicit change. I can just start typing. So let's say we want to say enter the text on a Pocket PC. So we can start tapping O, N, scroll down one to choose the word on, A, pocket, P, O, C, K, E. So notice the predictive power here. We are predicting the completion of the word pocket without having typed the last T. So pocket, typing the word letter P will give us PC further down. So some of the other features on the particular demo we see here, sometimes for the word, let's say, demonstrating. In this case, the recognition is perfect. But let's say how we want to type the word demonstration. It's kind of annoying to have to figure out, okay, I don't see the word demonstration on this list. And therefore, I need to find the letters for D, E, M, O, N, and so on and so forth. That's kind of a pain. So alternatively, you can just press the right arrow key to commit the next letter of the currently selected prediction. So in this case, if I press the right arrow key again, I will commit the next letter, which is currently set to M. So let me see if I can zoom in a little bit to make it easier. So over here, you'll notice the bold letters on the D and the E. This indicates that these are the two letters that have currently been constrained by the T9 prefix. So effectively, at this point, we are entering the letter M. So if we were to press the right arrow key at this point, it will enter the word M add it to the prefix and show only the words that starts out with D, E, M. Now, sometimes we will also make mistakes when we type these T9 entries. I mean, these keys are pretty small. Sometimes when we're trying to type fast, we make mistakes. That's not a problem. Just backspace over it. Press the left key to backspace. And basically, this is a whirlwind tour of what the particular user interface looks like on these type of devices.
So about the error correction, so this left to right mechanism works fine if the error is, as you say, it's in the suffix of the word. But if it's in the prefix, it's a bit more awkward
Yes.
to do that, right?
Yes.
So these guys in Huli, they have a different error correction interface where you basically break the word into letters and then you have random access into that word. You can just say go to that position and fix the letter and so on. So I'm wondering if that couldn't be used here as well.
It is possible. However, the thing we have to consider here is for Huli scenarios. So Huli is a desktop scenario for doing speech accessibility. Effectively, we want to enter text onto the desktop using speech alone without relying on the mouse, the keyboard, or any other input methods. In those cases, yes, we can say, I don't know the particular usage right now, but you can perhaps say, change letter 1 to C, or something like that. But on a device like this, we cannot assume the accuracy is reasonable. Therefore, even things like command and controls, we cannot assume that we are going to be able to correctly recognize a command to fix the errors. Therefore, instead of relying on speech, which is inherently inaccurate, to correct inaccurate speech, we are only going to rely on the keypad.
You could still borrow the idea. You could probably use the keyboard to navigate to that position.
Yes.
If you have a word that is 9 letters long, it's okay.
So as an example, let's say I say Kool-Aid. Your dictionary is going to find cool, C-O-O-L. But the product is with a K. So it's the first letter is the only one that's different.
Right.
How would I handle that? Erase the whole thing and type it in by hand?
So that is one option. It's doable. So this is one of the fallback methods. The other thing here is once you type it in once, it will be added to the dictionary, such that in future cases where we hear the word Kool-Aid, it will be spelled correctly.
Or give me the option for both of them?
Yes. So hopefully all these out-of-vocabulary words you only have to enter once. And in some cases, there are other schemes we can come up with to actually correct errors in the recognized word in a character-based level. However, this most likely will cause more confusion to the average user than it is worth. And even the advanced users, it's still somewhat questionable if this feature is worthwhile, since the likelihood of that happening may not be that high. However, if the usability studies suggest that this is an interesting feature to look at, that is something that we will need to look into. So the first question that many of you probably have on your mind is, why don't we actually display the entire recognition result at once instead of kind of this one word at a time interface? Well, there are actually a few reasons. Surprisingly, this interface actually reduces the number of keystrokes required to navigate to the misrecognitions. So in this particular model, the enter key, pressing the enter key, is roughly equivalent to moving the cursor to the right by one word. If we have no mistakes, so the perfect recognition, with a n-word utterance, we need n enter keys to fully enter the text. Whereas the other traditional model of displaying the entire utterance at a time, you don't need to type a single key. However, if there are some recognition mistakes, which is our assumption, then the effort to move the cursor back to the word that contains the error, correct it, and then move the cursor back could be up to 2n for moving it back to the first word and moving all the way to the end, another n.
Did you consider showing the entire thing and having like the cursor start out at the first word and I write, and so that like I can see the whole thing. I know that it's the fifth word that was mistake, so I just tap, and then I'm there instead of having to
hold on to that question for a minute. Hopefully by the end of the slide, it'll be addressed. Another issue with the traditional scheme without having a pointing device, such as a mouse, to highlight words, is sometimes the recognition errors occur kind of in groups. So in the example of, let's say, the actual speech is Mrs. Smith being recognized as this is Smith. We can't just select the word this and fix the error because we have a word segmentation problem. What we actually need to do is actually highlight both words, this is, and find alternates for that. So that additional highlighting is actually somewhat interesting in terms of UI design. How many more keys do you need to actually allow the user to be able to highlight a range of words and then select it? With the one word correction at a time, we don't have this problem because we will always have the proper word segmentation. The predictions that we get can show both the word this and Mrs. They don't have to have the same ending point. Another benefit of having this one word at a time approach is that we actually increase the perceived recognition accuracy. So let's say the word that we said is recognized speech. The recognizer has two hypotheses. One is recognized speech, one is rec a nice speech. And for some reason, the sequence rec a nice speech had higher probability, let's say. Now, if we were to look at the traditional method, that is 4 errors. But if we were to correct one word at a time, after telling the recognizer that the first word is recognized, so the first error, correcting the first error, the remainder of the speech is now correct. So we have reduced the word error rate, or the number of errors, from 4 down to 1. Another advantage of this model is that this is actually quite familiar to users of the existing text entry methods. This is how T9 works. This is how Multitap works. And in fact, we are able to seamlessly switch back and forth between just the plain T9 and the speech-assisted T9, primarily because we don't display the entire result at once. So to answer your question a little bit more directly, had we displayed the entire utterance, we could not have changed the rest of the sentence after the user commits the first word. At least that interaction may actually confuse the user. And there's actually there's another very important reason, which I'll get to a few slides later.
So if I correct, okay, so it says recognize. I guess that the first thing that's going to come up is the word rec, which is a single syllable.
Mm-hmm.
If I change that to recognize, it's going to say, oh, that's 3 syllables, let me move forward, my currency pointer or whatever you want to call it.
So
It'll know to move forward, not say, okay, let's just go on to the letter A now.
yes. So basically, the idea here, we'll see more examples of this later, but this is a speech record result lattice. What it does is it's a graph containing all the possible recognitions. So each path through this graph shows you a possible recognition that the recognizer thinks it might have heard. Once we commit the first word, saying that the first word is the word recognize, we have ruled out all paths that do not start out with the word recognize. So in that case, we will not have generated the hypothesis A.
I think there's still an argument for showing the best path at the same time, because so let's say it shows initially after you say it says recognize speech, recognize speech, right? And then it takes you to the first word. You say you don't want rec, but you want recognize. Then if you show the rest, now you go down a different path, and you can show recognize speech. And the advantage of that is if the sentence were longer, like recognize speech is hard or something, right?
Mm-hmm.
Then if you could allow for other UI things like a double click or commit to the entire phrase. So that way you don't have to, if the rest of the recognition is good, right, then you don't have to go word by word. So it may still be useful to show the best path as you go along.
We agree with that, and it is actually listed in one of the future works. Although there's actually another reason why sometimes that is tricky to implement. We'll get to that in a few slides.
I forgot how your demo went. Were you showing the completion for the current word or the embed completions for the current word as you were typing every character? So after I type RE, are you going to show me recognize right away?
Yes.
As
In fact,
opposed to-
after you just type the letter R, we have ruled out that.
Right.
So yes.
Okay.
I always see a small problem because people then your model people can speak once and they have to correct whole sentence. Right? But some people just they suppose they want to say recognize again. Then we will lost the previous whole sentence. Right.
Yes. So this is an issue if you want to speak again effectively.
Just for a few words, right?
Right.
The whole sentence.
So the current model right now does allow you to speak at any time you feel like. The issue there is that we actually ignore all the past results. So it is as if, okay, everything you've committed up to now stays. But from now on, we're going to start a new utterance. So if you were to have said a longer sentence earlier, where we may lose some of the end of that sentence. So generally, when we use a system like this, and this is actually generally the case with SMS messages, we try to limit the number of words we say at a time. For SMS messages, which averages around 5 words or so per message, this is fine.
Cool. I really like your perceived, accuracy thing argument. So what would be the tip point that if your accuracy is X, Y, Z, and how many words you would actually speak, and then with this correction mechanism, what would be the tip point? You can say you just say 1 word at a time and you type, or you can say 3 words on average, or you can say 5. So what would be the balance point for the perceived accuracy improvement?
So that's an experiment that we still would like to conduct.
You can run this actually independent of the whole thing. Given the accuracy of 90%,
Yes.
20%, then you have the balance point of maybe 5 words, 3 words, or 2 words.
So there are many factors we need to kind of address first before I can really answer this question. One is, what's the evaluation criteria? Is it the word? We'll talk a little bit more about this later. Word accuracy? Is it the actual entry time? What is it? And also, it depends, the result depends highly on the actual lattice that you get back. And so it's kind of difficult to say at this time. And there are another factor, which is how fast does speech recognition actually run on these devices? When we looked at the demo, it looked pretty good. It's actually not that fast, as we will find out.
So what's your throughput right now, on average?
I haven't measured that. That's a number I would really love to have had, but we have not measured it.
But basically, when you see the first word, the system is still running at the end of the sentence. So if you have to show the whole sentence, you need to wait longer, which is probably not good, because it may be wrong.
I'll get you that.
Or if you do the other way around, you do the T9 first, and have the restrict pass in the search space in XR, then your search will be much faster.
That's a very good point. I'll get to that in the future ones. So how do we actually generate the list of predictions and rank them? So we get to make it robust, we actually combine both the results from the speech recognition lattice and the results from the n-gram based on context. So let's say if the committed word so far is "this is," for the sentence, "this is a speech recognition," or something like that. Let's say this is a returned lattice from the recognizer. Because we know the committed words in the beginning are "this is," the only candidate nodes for which we can actually be in at this point are these two blue nodes here. That corresponds to "this is" and "this is." We cannot be in the path that starts out with "misses." And therefore, based on that, we can then determine the set of candidate words that follow these candidate nodes to be speech, beach, and bee. To actually find the probability of each of these candidate words, we first measure the forward probability along the path to the candidate node, multiply that by the transition probability. So in this case for speech, it's 1. Whereas for the case of beach versus bee, we have different transition probabilities. And then at the very end, look at the reverse probability, namely, what's the probability of completing the rest of the utterance from that node on. So using that, we can then provide a score. In this case, we represent it in the log domain, hence we see the negative numbers for each of the candidate words, and then return that as part of the prediction list to the user. We can also use the n-gram context. Specifically, in this case, we are using a trigram back-off language model, which would say look at the words that are possible following "this is" with high probability. Take that list, combine with the words that are likely to follow the word "is" by itself, and combine that with just the entire vocabulary. Each one of these sets are weighted by the appropriate probabilities. Now, since these models are actually somewhat large, in the case of the model that we are using, it's roughly 7 megabytes worth, and these devices generally don't have that much space to spare. We are actually reusing the language model from the speech recognizer, so we don't introduce another model that we load into memory. So based on the lattice results and the n-gram results, we can then combine the two lists and generate the prediction. Now, there's actually something else we can do to actually improve the results. I don't know if you noticed, but sometimes when you look at the prediction list, we have words that are acoustically nothing like the word that you actually said. Those words are generally generated from the n-gram context. which currently does not factor in the acoustic evidence. It is possible to re-rank the words generated by the n-gram context, factoring in the acoustic evidence such that we provide more realistic results to the user.
So do I understand correctly that you're not using strictly the lattice?
We are not using only the lattice. We're combining the lattice with the n-gram predictions to make the system more robust to speech recognition errors.
So the reason there is that the lattices don't have words, right?
So we need to do this to handle out of lattice words. So similar to out of vocabulary words with T9, where if there's a word that's not in the dictionary, there's no easy way to enter that word. If there's a word that's not in the speech recognition result lattice, there's no easy way for me to predict that's the word the user actually wants. And since recognition accuracy, we're assuming, is not perfect, the lattice accuracy is not perfect, we need to supplement the predictions from the lattice with just generic back-off language model.
So do you do that as you start typing in the letters of the new word and you realize that there's no corresponding word in the lattice?
So basic idea is, let's say, suppose I start, at this point, I start typing the word SC instead of SP. We will realize that, okay, of my 3 possible lattice candidates, none of them start with SC. And therefore, okay, I've fallen off the lattice. I don't know what word the user meant. Therefore, we will go to the n-gram context to then list the words that start out with SC that are most probable to follow the sentence, this is.
So you wait to follow the lattice to look at the n-gram context, or you just always have the union sitting there?
Currently, we actually have the union at all times. However, the implement.
Odd for the user, right? If I had a list of like 2 words and I press a button and suddenly it blows up, right? It would kind of
Although,
jarring.
Just expect that today.
oh yeah, although there are.
It doesn't blow up as such because we always fire the list which comes from the lattice. If there is space in the list beyond what comes from the lattice, we basically supplement it with the n-gram probability. So you'll always see 4. You don't really know which ones came from the lattice, which ones came from it. But the n-gram ones will never supersede the ones from the lattice. That is the
current implementation, yes. Although that's something that we may or may not want to do.
There's some challenge here potentially in building that n-gram model, just because the way people type text messages, with all their abbreviations and funny little UR, blah 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 blah.
Yes.
Is there a data set you guys are using for this kind of stuff?
Do you have any what?
Is there a special data set of like text message entry that you can use for this?
That is something that we're looking to acquire. There are some out there. We are not quite sure what are the legal issues of using them at this point.
Yeah, I was going to ask where you got the n-gram.
The language model right now is trained on a Wall Street style data. It's not perfect, and therefore we actually expect the performance to further improve when we have a better matched data set.
It's actually more like news and some of the email information. So it's a combination of different things, but certainly not SMS type messages.
Do you have a letter n-gram in there anywhere? Is there a plan for a letter n-gram at some point?
So letter n-gram, the idea here is, can we predict the next letter based on the previous letters? This is an idea that was explored in a system called LetterWise that is actually that is also deployed today. Currently, we are not looking into that, but that is something that we can integrate into the system.
If the user falls completely off the lattice, choosing a word that's not in there, do you let them get back into the lattice?
I'll get to that.
Well, so the list is a union of n-gram and lattice results, right?
Yes.
So do you need to do some kind of normalization to make the ranking correct?
Currently, we always rank the n-gram behind the lattice results, so you don't need an explicit normalization. However, that is an assumption that we are questioning. There may be cases, especially once we incorporate the acoustic evidence, re-ranking the n-grams based on what it actually said. Once we do that, we may want to consider, in some cases, to bring up the n-gram predictions ahead of the lattice predictions. At that point, we do need to think about normalization. So another advantage of this particular system is that, as we've seen, the T9 prefix hints filters out the list from initially the entire vocabulary size down to the target word pretty quickly. And if the list is sorted by the probability given by the lattice and by the n-gram context, we can get there even faster than just using T9 alone. So in the best case, when the recognizer recognizes the sentence perfectly, we had to press OK for each of these words. And we can go through that pretty quickly. In general, on the average case with a reasonable, somewhat, a little bit of background noise, we may need to provide a few T9 prefix hints or to use the up and down arrow to select the alternate a few times. The interesting thing here is, let's assume we have 100% word error rate. So in the case of recognized speech, we got rec-a-nice speech, 100% word error rate. We can still do better using speech than not using speech because we have information from the lattice. But what if the word is not even in the lattice? Well, if we incorporate the acoustic evidence into our n-gram predictions, remember T9 has some ambiguities, some key sequences, for example, home and good share the same sequence. We should be able to use the acoustic evidence to rank these two alternates such that the user does not have to then select the correct one. So we can use speech to correct ambiguities in T9. So even with 100% word error rate, where none of the word in the lattice is correct, speech can still be useful. And in the absolute worst case imaginable, let's say we have an adversary giving us really crazy, weird results to interfere with the T9 prediction list. We might sometimes bring up results that are kind of pushing down the correct word further down the list. But generally, we do not expect that to happen.
Are you factoring in the time that you've spent speaking in the worst case? I mean, so it would seem to be guaranteedly worse than T9 because you've wasted the time saying these words.
Yes, so we have wasted the time to say these words. But as you can generally is the case, speaking takes about 1 to 2 seconds, whereas the correction part takes on the order of 10, maybe even longer. So it's relatively insignificant.
I think it's misleading to say that it's about the same as predictive T9 when it's definitely worse than.
In the absolute worst case, when we have the misleading recognitions. In the 100% word error rate case, we can still be better.
Sure.
So it depends on how you define about. But approximately the same. A little bit worse.
You can certainly imagine situations where the worst case is at least slightly worse than just doing K9.
Right, so I agree with the word 100% error rate, but if you're going to define a worst case, then you should give it a real worst.
Quantify that a little bit. Yeah.
Sure, that's fine. So out of lattice words, we can handle by falling back to the n-gram predictions. But what if we have actually a word that is not even in the vocabulary? So with T9, if it's not in the vocabulary, there's no easy way to do it. So let's look at how SpeechPad actually does this on the Pocket PC. So let's say I want to enter the sentence, this is an OOV word. This is a OOV word. So this is a, now I can start typing OOV since I don't see it. So O-O-V, to restrict the prediction list to only those words that start with exactly, that only have 3 characters. I can press a space key here. And I still don't see the word OOV. But notice there's the keyboard option. If I scroll to that, it'll bring up the soft keyboard on the Pocket PC, in which case I can then type in O-O-V, enter, and then I come back. I think I said this is an OOV word or something like that. So notice word is again recognized. We're back on the lattice.
That little keyboard's not going to work.
I understand.
If I'm using my thumb, there's no way.
Yes. So, yes. So in this case, that's due to time restrictions. We decided to use a soft keyboard on the Pocket PC. On a device such as a smartphone, what we would like to do is to fall back to multitap. So basically, when you click, instead of keyboard there, you would perhaps have the word multitap option. It will switch the mode temporarily to multitap. After you commit that word, it'll switch back to this multimodal entry method.
I have a question about, so I mean, when you put OOV in, I mean, your recognizer doesn't know that that's an abbreviation. It thinks it's OOV, right? So if you try to re-decode with OOV in there, it's not going to put you in the right place with respect to the rest of the.
Well, I'll get to that.
Oh, okay.
So, just a little bit of a sidetrack, but even on regular T9, with whatever the shift of magneto, one of the most annoying things is once you T9 to the end of a word, it's not in the vocabulary, then you manually need to switch to multitap, delete the word, type it in, and then manually switch back.
Yes.
And your suggestion here, there's no reason you couldn't add it on top of T9, even if you have no speech. And I think it's big.
Right. So currently, with the existing systems, we have to do a manual switch if we enter a word that is not in the dictionary. With the particular implementation today, the switching part is now automatic. However, it's still kind of annoying that you have to retype the word. There are some ideas that we have where we can perhaps use the acoustic evidence to do some sort of inverse speech to text. So instead of letter to speech, we do the inverse to get speech to text and predict the spelling based on the acoustic evidence. And given the constraints, the T9 prefix, we can then hypothesize which one of these spellings is correct. That is a lot of work for future research. So let's go back and see why we can recover from the lattice when we have an OOV word. So as people pointed out, I'm not going to be able to know that the word is actually OOV because what I entered is OOV. So what the current implementation does is we basically relax the lattice traversal algorithm such that instead of forcing exact match to determine the candidate nodes, we allow mistakes, and we will penalize those paths, the probability at the candidate nodes, depending on the number of mistakes we made. So effectively, this is an edit distance concept. So let's suppose the word that we actually entered was this was, and the lattice is given here. So if we were to traverse to this node here, so this is correct, but instead of having is, we have a substitution error with was. So that is basically reduces the forward probability to this particular candidate node. Likewise for this nodes. It is also possible for us to get to this and have a deletion or an insertion, depending on the way you look at it, inserting the word was without advancing in the lattice. So this is also one word error. Some of the other error rates we can get is 2 errors if we were to be still stuck here. This would be 2 errors, 2 errors. To get here, we need 3 errors. So if we were to factor in the penalties, effectively, we have all of these words as possible candidate nodes, just with different forward probabilities. And if we were to take the candidate words, compute its probability, we might have something like this. So that is actually how the system currently recovers when you enter a word that is not in the lattice. Now, if it is OOV word, it's obviously not in the lattice, but this actually applies to even when you were to take a prediction from just the n-grams.
So, sorry. You can measure how many times after traversing the OV you end up at the right node in the lattice, right? Like, for example, here, the OV was, let's say it was.
Yes.
And using your algorithm, I should be able to identify that now I should be calculating the posterior probabilities of words at those two nodes following is, right?
Right. But
So that's the ideal scenario. But
yes.
My question is, how often does this happen as opposed to making a mistake and ending up at some other node in the lattice?
It is quite possible that we end up somewhere else because the durations may be different. In this case, was and is are both single phoneme words. But let's say if instead of is, we get isthmus as the actual word or something like that. In that case, it's more likely for us to be further down in the lattice than just the next node. So that's actually why instead of using the the word edit distance, it would be nice to actually use the phone edit distance between the path to a candidate node and the phone string for what has been entered. This is currently not implemented, but we expect if we were to change the implementation to that, we will significantly improve the performance of lattice recovery.
If the word is in the vocabulary but not in the lattice, then after the user gets it, selects it, do you use n-gram scores to help pick the right reentry point into the lattice?
So if the word is in the vocabulary but not in the lattice, we use the n-gram scores to weigh the predictions. Currently, the algorithm does not. Instead, what it does is it still generates a list of, it kind of does it in a different way. It still generates a list of words predicted by the lattice and combine it with just the n-gram predictions. So we're not going to use the n-gram scores in the lattice, but we will use it from the n-gram, separately in the n-gram.
But that's a good idea, I think. I think that's probably a slightly better way of doing it. Right?
So that's something that we can look into, but that's not the current implementation. So how do we actually make this thing respond so fast? Can we switch to the Pocket PC again? So in this case, let's say we want to just speak something. This is a test of speech recognition. Did you hear that beep? So that's when the recognizer actually finished recognizing the sentence. It is not immediate at all. So how do we actually have predictions before the recognizer finished the recognition of the entire utterance? So what we do is actually use the hypothesis lattice, the lattice from the hypothesis events. These are effectively the partial lattice representing what the recognizer has processed up to now. So basically, using the hypothesis lattice, we allow the recognizer to continue processing the remainder of the speech in the background. So instead of having a variable latency that depends on the difficulty of the speech and the length of the speech, we now have a fixed 500 millisecond delay. We choose 500 milliseconds because it gives us a sufficient time for the engine to actually give us something reasonable while not kind of distracting the user too much and making them wait. So in the worst case, 500 milliseconds may not even be enough. The engine may not even have generated any hypothesis in that amount of time. That's okay. We just go back to the n-grams and use only the n-gram predictions for the prediction list. And as the user starts entering the words, hopefully the recognizer will have more time to catch up. And in many cases, it has enough time to catch up just entering the first letter. So after we enter the first letter for the word, the recognizer says, "Ooh, I have a new hypothesis for you." And the system can then take that new hypothesis and do the same traversal to find the candidate words that matches the prefix. So notice that this particular optimization is only possible with the sequential commit style of input. If we were to display the entire recognition result at once, you'll have to wait. This optimization would not have been possible.
So I guess when you do this, you just use forward score only?
This is something that we are investigating. Currently, we are doing forward score, transition score, and the backward score. However, we're not quite sure. Exactly. We're not quite sure what that backward score means right now. That's a. Actually, Ricky may be able to answer what that means right now.
It's the backward scores you get if you assume that, however far you are, that is the end. You imagine
it's the backward score, assuming that the recognition ended at whatever time the hypothesis was generated. Right. So I mean, it's an approximation, but it's
an approximation.
Better than nothing.
So if, for example, a hypothesis was 1 word long, then your backward score is equal to 1.
Yeah. So it's an approximation. It's not perfect, but we will try to leverage as much information as we have at that point so that we don't have to make the user wait.
So you're saying the speech recognition will catch up pretty quickly as the user types in the first letter, right?
We're saying that the user is generally slower than the recognizer.
So I think maybe in terms of user interfaces, it's better not even to have the beep, so users don't know about this.
The beep is added. In fact, a lot of the UI is currently there just so that I know what's happening. Yes, we do not plan on having the beep in the actual product. And likewise, there are a lot of subtleties. So for example, right now, I don't know if a word is coming from the lattice or the n-gram. Sometimes it mixes so well. If I actually change the color a little bit so I know which one this word is coming from.
I know that we normally don't provide a full lattice with hypotheses. When you upgraded that, did you notice any slowdown?
There is a little bit of slowdown. So it's not, I'm estimating about 10-20% slowdown, although I have not measured this. To compensate for that slowdown, there are things we can do. Instead of having the lattice, instead of requesting the lattice to be generated for each hypothesis event, if we can modify the engine code a bit such that the application can request for lattice on demand, that will actually speed up and reduce the overhead. So for example, 500 milliseconds after the user releases the record button, the application can ask the engine, okay, give me your latest lattice, whatever that happens to be. The engine hands it back. After the user clicks a T9 prefix key or commits a word, the application asks the engine, give me your latest lattice. At that point, if the engine has a new lattice, it returns it, and the application processes it. If the engine still has not generated a new lattice at that point, it just says, sorry, no new lattice, and the application continues using the old lattice such that we don't have to generate lattices that are ended up thrown away.
But are these lattices guaranteed to overlap? Like, if you use the lattice, you have a prefix, you're somewhere at some nodes in the lattice, and here comes a new lattice that has nothing to do with that.
It is certainly possible. There are no guarantees that the engine will not prune away paths that existed before in earlier lattices. However, since we can recover from out-of-lattice errors, we're fine.
So each time you get a new lattice, you have to do the search?
We actually redo the traversal to recompute the candidate nodes.
Yeah, right. So there's something that he has done which is quite cool, which is that sometimes you have a hypothesis lattice and you have generated the alternate list from it, and you don't want to switch it on the user all of a sudden. But at the next time the user types something, he expects the list to change anyway. So at that time he changes to a new hypothesis lattice, and you don't actually know why the list changed, because you typed something or because you got a new lattice. So it's pretty.
So the only thing you need to make sure that some hypothesis that was on the old list, which the user liked, will suddenly disappear.
Well, if the user liked a hypothesis on that list, most likely he or she would have used the up or down button. At that point, I don't change it. But if you press a letter, hey, I have the right to change it. So the way you can notice this is if you, let's say, press a letter and then backspace over that letter, you may not get the same list back.
Since you're not showing the rest of the subtree, right, you don't have to show that rest of the subtree changing every time you put in a new thing. So you just see a list of words, then a new list of words. So
exactly. So that is one trick to actually make the system perform on devices where we don't have the same computing power, computing resources as desktop machines today. So in terms of actually evaluating the system, we haven't spent a whole lot of time in this area due to various priority changes. We can look at the average keystrokes and entry rate and compare them with existing systems, such as T9. We can also look at the recognition accuracy and how it depends, how it varies on different scenarios. Now, it's kind of interesting to perform actual usability studies to get these numbers. But since any tiny little change to the system can potentially change these metrics quite a bit, we don't want to have to perform a usability study after every single time we make a little change to the system. Instead, it would be desirable to have a way to kind of estimate these values given the results from previous usability studies. So one idea that we have is to basically look into previous usability studies, break down the individual times. How long does it take for a user to press a key? How long does it take for a user to press the OK button? Look at it in a context-dependent way and be able to simulate the effect of user pressing keys in order to to enter a text.
What is the standard in cases like this? Because I can imagine that although in two different systems you enter the text at the same speed, one may cause more fatigue, for instance, on the user and not be as pleasant.
Yes. So the issue of cognitive load, how much strain there is on the user. Does the user have to move their eyes up and down a lot of times? These things are not easily measurable by just looking at, let's say, the final task completion time. So instead, generally what people do is to do a qualitative survey afterwards, asking the user, how tired are you? Or making them perform some other task in the same time. In some HCI literature, there's also techniques where they make the user do two tasks at once and see how the performance on the second task degrade as they perform the first task. So they switch the first task and see how the performance on second task degrade. These are all attempts at trying to capture the cognitive load, but it's not an exact science. That is actually one of them. You don't want to know. That is actually one of them. Drive in a simulator. How many times do you cross the line? That is actually one of them. So using these simulation techniques, it would be interesting. We can conduct many, many more experiments to actually measure the effectiveness of the system. One such example is to actually check to see if we have graceful degradation as promised or as we suspect we will. So we can take speech, add it with varying amounts of noise, and look at the text entry time. That is an interesting experiment that will provide some interesting insight into the particular system.
You're not suggesting that you're going to do everything by simulation, right? You're going to at least do one usability experiment too. Okay.
We would perform one usability experiment to measure the individual times for clicks and kind of for the user to look at the prediction list and so on and so forth. We will use that time, which are actually measured times, to add parameters into the simulation. Now, granted, before we release the product, or perhaps even every so often, we still want to make actual usability tests to see if our numbers are in the ballpark. Usability tests in itself is not an exact science. Different users have different times. So we cannot, with the simulation, we actually have lower variance than if we were to use it perform the tests on real users.
And are you planning on comparing In that test, I assume you're also planning on comparing that against all the other ones, like T9.
Yes. Yes.
I mean, I think in terms of getting people to use it, there's probably two main things that people are going to care about. One is that, I mean, there's pretty good numbers out about T9 and various speeds of T9 and variants, and there's world competitions and all this stuff, right? So there's pure speed. And then the other big one is the last thing that you're mentioning is the robustness against noise, simply because, a lot of the times that you do text message or situations where it is at least somewhat noisy.
Yes.
But I think that if you can give clear numbers on those things, I don't think that, I mean, like every single aspect, level of cognitive load, I mean, those are important things. I don't mean to discount them, and a community like Kai or WISP would probably care a lot about that. But in terms of getting users to say, like, yeah, I'd rather use this than T9, I think those are things you're going to convince them.
Yes. Those are tests that we would really like to run.
Yeah, that's privacy too. Yeah, that's a good point. Yeah.
The what?
There's the issue of
In
privacy.
the meeting, you don't want to really talk. You want
Yes.
to
So that's why there's a nice graceful fallback to just using text alone without even having to explicitly switch modes.
So I think we can be pretty modest in our goals, which is that we can say we want few of the users or some fraction of the users to use it fraction of the times that they use this, and because not necessarily all the users all the time.
Well, it is much easier. People just automatically switch to those.
I guess the other comment I would make is that I think your biggest competition is probably the MMS stuff that's coming out in terms of like short audio messages sent back and forth, because it's kind of like if you're in a situation where you could say the word out loud, then you might just send the little audio message.
Yes, so MMS is an interesting new development where users can actually send short audio clips to other cell phone users. However, this is a kind of one of those interesting things about technology. A lot of times you wonder, why don't people just call the other person when you have a phone in front of you? Why do they actually prefer SMS messages? It's asynchronous. That is actually one of the biggest things. And this is true for MMS messages too. So
it's cheap.
Actually, it's more expensive for a lot of people than
SMS is cheaper than a phone call.
No, we'll see, but it's an interesting development.
In the U.S.
In the U.S., not in Asia. In Asia, the reason is that it's cheaper.
Oh, I see.
In Europe, it's much cheaper to send SMS than to make a call.
It's cheaper in Europe as well?
Yes.
So I don't know why in the U.S. it's more expensive. Right?
Okay, yes.
You're going to have any evaluation yet? That's what you're...
What we have done instead of focusing on evaluation this summer, is to actually attempt to work more on the technology transfer. So far, we have shown the demo to quite a few people and received pretty positive feedback so far. We presented to Deng Ling in a MSR speech special group presentation. We showed it to individuals in private, and we even showed it to Bill Gates in the demo days. And so based on some of the feedback we have received, and an email from Bill always helps, we are currently engaging in discussions with the mobile and embedded devices group to see what we can do to actually make this part of the next release of Pocket PCs and smartphones. And we are also currently looking into filing patents on a lot of these ideas that are in this project. So in terms of the next steps, we need to think about what are the additional optimizations we want to make in order to incorporate this particular demo onto smartphone devices which have even less CPU and less memory. What UI improvements do we need to make to actually make this usable to the users? Part of that involves running actual usability studies. We have so far gotten some informal usability. We have done some informal usability studies to come up with a current design. And in fact, a previous earlier design of this had a horizontal prediction list rather than the vertical drop-down that you see today. And just making that one tiny little change caused a significant difference in the perceived usefulness of this particular system. And as always, we can always improve the prediction and the ranking, the lattice recovery, and a lot of the underlying basic technologies. I hope that answers your question. Let me come back to the previous slide. That's a quote from his email. So in terms of the actual steps that we can work on, there are issues of inverse text normalization to think about. Right now, if you were to say the number 123, I don't want to see it spelled out. How can we actually combine keypad and that type of speech? That's something to think about. How can we make this globalizable? How can we localize it to other languages? The European language, Western European languages are relatively straightforward. But what about Chinese? Do we use pinging? Do we use strokes? What do we use? In terms of the user interface, as suggested, we can optionally show the completion for the entire phrase once the recognizer finishes recognizing and if the confidence is sufficiently high. So the user can perhaps only hold down on the right arrow key for perhaps half a second to commit the rest of the sentence. That's something to think about. However, there are some usability concerns that we want to look into through usability study tests. And the point that was raised earlier about SMS abbreviations. People using SMS because of the 160-character limit oftentimes don't type in English. They type in these tech lingo, where great, for example, may be spelled out as GR8. So what can we do for those users who want to conserve their SMS bandwidth, where they have to pay for each message that they send? So ideas there include perhaps having an option at the very end before you send the message to compress the message using the SMS lingo and perhaps using other abbreviation functionalities. In terms of performance and accuracy, we really want to do LM adaptation on SMS-like data and on data gathered from the actual person, from the actual user, from the device, and from their desktop. Likewise, we want to do AM adaptation to the user's voice recorded on the device. Currently, the speaker-independent model is working, but we can do a lot better by adapting to the user's speech. In terms of other optimizations, as was pointed out earlier, if we know the keystrokes, we can actually change the search path a bit. We can prune out paths that don't match the committed word sequence. So there are some ideas there that we are going to look into.
Question. So how are you going to do, I think for T9, you can adapt the vocabulary, right? Yeah. If I type a new word, T9 remembers.
Yes.
So you would want something like that on the speech side too, but there you would need the pronunciation for the word.
Yeah.
How would you get that?
So there's the LTS, letter-to-speech module that's currently in the Yakima CE recognition system.
But that would need to be on the device at that point, right?
Yes. So that's one is we can put it on the device. If we cannot fit it onto the device, which I believe it is currently, is that correct, Ricky? Okay. Assuming it's not on the device, what we can do is to have the pronunciation be added when you perform active sync with the desktop. So that's part of the adaptation effort can be done in conjunction with the desktop during active sync. But I think it is there because of the contact list issue.
For names and stuff.
Yeah, pretty sure it's there. So in summary, the project is about combining speech and keypad inputs to enable efficient and robust text entry. And hopefully the SpeechPad demo application has shown that this is doable today. And finally, I would like to acknowledge my mentor, Malind, Alex, and Phil, who is not here, for giving me the opportunity to work on this project, to go to the BuildG demo days, and many of the other opportunities that I would never have expected coming here. I'd like to thank Drew, Ricky, Eric, and Julian for all the technical assistance they provided. Sometimes I would just camp out in their office until something works. And of course, to Tim, Robert, K1, Jason, another Robert, and Walter for the discussions that led to many of the ideas that we have today. So at this point, before I let you guys play with the actual device, are there any other questions?
What what happens in the scenario where someone mistakenly commits to a word, right? So in T9, you can always sort of go back, right? And then, delete that word and then continue on. But you have to keep around all of that state information in order for you to handle that well, right? So what do you do?
So currently when the user commits an incorrect word, what they can do is actually press the left arrow key to backspace over the entire word and then just start typing again. That will work because the lattice code supports recovery. So it is as if, okay, we have an insertion of this extra word and the prediction will not be as accurate, but it'll still work. Right. There are other alternatives where we can actually keep track of the actual words that are inserted. So if the user backs over that word, we are aware of that, and that is also doable.
But that's if you notice it immediately, right? I mean, like, if you've already committed to several words, perhaps even several phrases, and then you notice, oops, I picked that wrong word.
It is possible to store the lattice for the particular phrase. However, on these limited devices, it's questionable what value actually introduces.
So what real-world scenarios do you envisage people actually choosing to use the speech component in here? So, what environments do you think that people would use this?
I am hoping that this will be useful for pretty much all SMS scenarios, including the ones where it's fairly noisy, once we implement a lot of the other algorithms that we want.
It's already been mentioned that one reason that people use SMS is that it's not disruptive and you don't have to say things out loud, so it's more private, things like that. Do you have a good feeling that do you have any feedback from users that there are situations where they would choose to speak things if they could?
So this is where we would need to do additional market research to figure out. We haven't done that yet.
Right. So one thing is that we haven't done the market research or anything like that. But I did show this at MSR Tech Fest, and a lot of people actually stopped by and said, this will be great because I hate T9. I mean, I'm sure there are lots of people who love T9, and I don't think we can get everybody to use this kind of a system, and even people who like it won't use it all the time. But I certainly feel that based on that interaction that I had with people who stopped by, maybe they're just being nice, but I don't think.
Well, Samsung.
That I think there will be certainly a subsection of the user population which will want to use that.
So Samsung already has a phone that allows speech dictation for SMS messages.
Yeah, I'm just curious as to what environment, like who does it and when.
Yeah.
I would love to know the answer to that question too.
And I think one of the theories I have is it's just a theory, I haven't tested it out, is that, I mean, yes, we think from the point of view of the sender that, okay, sender doesn't want it to be known, but sometimes the recipient is in a meeting, and you can't call him. You have to send him a text message. And maybe I'm in my quiet office, but I still cannot call because he's not going to pick up. So maybe that's one scenario where we can think of it. And I mean, it's like for novices, I think T9 could be somewhat daunting, or any kind of user interface. So for them, this might be thought of as kind of a simpler way of doing T9.
Well, I can think right off the bat, if I had it, I would be using it when I do like the memos or the task, add a task to the task list. That would be a really easy one. You do email on your Pocket PC. I can see using that. Half the things that you'd sync with Outlook, this would be very useful for.
Writing the podcast.
Maybe not because.
Hey, remember we can have. We are fairly robust to a relatively high word error rate. And I've actually tried this. Sometimes it works too accurately. I have to mumble a bit to demonstrate the system. Otherwise, like, okay, that's kind of boring. So it's actually fairly accurate to even some of the noisy conditions, since we're not relying on the top result. We're relying on the entire lattice result.
Yeah, well, we demonstrated this to Dan Lin. He was shocked that it worked so well because there were like 5 people talking right next to him.
That's
I think this is very natural to, especially for like Japanese people who already used to do the sequential commit with the typing. So this is very kind of intuitive for me. And maybe you can talk to like people at IME team who have lots of experience with the UI and similar issues that you're dealing with the sequential command.
So currently we have talked to yes. We have talked to Jason here, who hopefully will help us figure out.
My team owns all the IMEs on the mobile devices.
So hopefully you'll be able to help us figure out what's a good user interface. Right now, this is just a prototype. We have a lot more work to do to actually make it into a usable product. Other questions? If not, time to play with the devices.